So today we're talking about Chapter 2, Section 5, Applications of Exponential Decay. Alright, so in 2.4 we talked about exponential growth. Now we're going to be talking about exponential decay. And well, I think I've said it a lot in this course, but I'm going to say it again if I haven't. I really like this course because it's there's not too much uh, like esoteric, abstract math involved. We actually see what we're using and why we use it, and it's pretty cool, especially with this particular section because well the problems are real world stuff. Alrighty. Alright, so here we go. Starting from the top. We don't necessarily have to read over this. Let's not read over that. But we will talk about radioactive decay down here at the bottom. So let me move that out of the way for a second. So radioactive decay, radioactive isotopes decay exponentially. That is, they're continuously decaying at a rate that is proportional to the amount present. And that's just how all radioactive isotopes are. And oh, that's what I probably missed. Okay, so yeah, I knew there was a reason why I snipped that. Let's look here. I mean, we could talk about the population and stuff, but really want to look at the equation here. Okay, this equation has to deal with uh, exponential decay, more or less, right? We have dp over dt, and that's equal to a negative k, which we know so far as a constant, right? And then times p. What is that p? Well, that's the function, right? Because the function's name is p, so it's p. And then we'll see that this function where k is greater than 0 shows that p to be decreasing or decaying as a function of time, and the solution is this particular function here. And so when we talk about solution, we're talking about the solution to the differential equation, which honestly is a concept that is like ultra covered in a class after Calculus 3 called differential equations. So we're kind of jumping ahead quite a bit to the fun stuff, but that's okay. And when I say fun, I mean kind of hard, but again, that's okay. This textbook lays it out in a way that we can understand it better. So let's just start with the radioactive decay of strontium 90. So strontium 90 has a continuous decay rate of 2.8% per year. The rate of change of an oh, maybe I should put the questions too, huh? Let's put these questions down here. There we go. All right, now we know what we're doing with this problem. The rate of change of an amount n of this radioactive isotope is given by dn over dt is equal to a negative 0.28 n. Again, n is the function, right? So A, find the function that satisfies the equation. Well, we saw that on the previous page when we go from a differential equation, right, dp over dt, and it's going to be equal to negative kp. Well, to write a function for that, we just write, the whatever the function's name is, and then naught, right, a sub-zero. So p naught, and then e to the negative kt. So in this particular case, what is my function's name? Well, my function's name is n. So it would be n naught e to the negative, and then we have the k already given to us. Again, looking on the previous page, k is the number in front of the name of the function. So k in this particular case is just negative 0.028. And let me actually do this instead of having to flip-flop back and forth. We'll just snip this, or that, what I just said rather. Alrighty, so we have an equation in this form, and we need to put it into this form. We need to have we need to write the equation. So I think it's gonna be good the way I set this up. Let's see, move this over here. I'm just gonna put it right underneath our notes here. So this is for A, For A, my differential equation is d capital N over dt, and that's equal to a negative 0.028 n. Okay, so I'm going to run out of room, so we're going to put this slightly under it. How about that? And if I want to write it in this form, well, I just have to follow along. Okay, so my function's name is n, so it's going to be n naught. So we're going to say n of t. So we're going to say n of t. That's equal to n naught, and then e, well, e is just e to the negative k. Well, k in this particular form is right here, right, following along with this equation. So negative 0.028, and then t. Right? And that's that. So that is a function that satisfies that equation. And honestly, it's probably a lot easier than I explained it, and I have a tendency to over-explain things, but oh well. So suppose that 1,000 grams of strontium-90 is present at time t equals 0. How much will remain after 70 years? All right, so we're going to put down 1,000 for n naught, because again, so in this particular case, where are our unknowns? So in our function, we have an unknown here, we have an unknown here, and we have an unknown here. So we have 3 unknowns. But in this problem, it's giving us the initial amount, so that's going to be n naught, and it's giving us the time, which is t equals 0. So we just put 0 for t. So we can just fill in this equation. Well, we're going to have n of 70, and that is equal to, my n naught is 1,000, and then e again is just e to the negative 0.028, and then times t, which is 0, which is going to be 0. So we end up with, I'm sorry, no. B, oh shoot, okay, I'm sorry, I messed that one up. So my time, my initial amount is 1,000 at t equals 0. We want to know how much remains after 70 years. Sorry about that. So we put 70 for that. We already have the initial amount. Okay. So now we can solve it, and this just becomes, and I got to do behind the scenes calculator work. One moment. So 140.86. All right. So about 140.86 grams will be left of the strontium after 70 years. Just simple plug and chug there. And C and D, probably going to put that on another page. All right, so C, find the rate of change of the amount of strontium-90 after 70 years. All right, so we have to find the rate of change. Okay, so we're trying to find the derivative, and this is pretty good because our equation was, well, rather our initial derivative here, right? Our derivative that we have is this. This is indeed the incomplete derivative of my strontium-90. I say it's incomplete because we have the n right here. Okay, that n again is just the name of the function, so it's kind of like saying, you know, negative 0.028 times f of x, right? At least in this particular case, my function's name is n, so it's going to be times this. Right? Well, not necessarily. It's going to be times this, but we're going to write this right here. So I'm going to have to do some flipping back and forth. Let's see. Okay, so again, my initial equation's here. So if I were to write this as, n prime, we would say n prime of t. We're going to go ahead and start with the negative 0. I'm already out of room. Let's move it down. All right, so D is going to have to just get its own page as well. So a negative 0.028 n. Again, all I did was just simply rewrite this. Okay, but now I'm going to have to replace this n right here with what n is. Well, n, we said, was this. So n naught e to that. Okay, so I can memorize that. So it's going to be that times n naught. So n naught e to the negative 0.028 and then times t. All right. Well, we have to figure out, we know what our original amount of strontium is, right? We have 1,000 grams, so that's going to be our n naught, so we can move that over as well. So we can erase this n naught and put a 1,000 there. Well, this is working nice. Okay, so 1,000. Yeah, let's make it bigger. So now we have 1,000 times e to the negative 0.028 t, right? And then I'm just going to have to, combine them. So I'm basically just going to multiply this times this, right? Because, there's nothing I can do with the e, so it's just, 2.8% of 1,000? That's easy, it's 28, so we can do that in our head. So we've got 28 e to the negative 0.028 t. And that is our rate of change. That is our derivative. So with that derivative, with that rate of change, we are now able to complete the problem. So we found the rate of change. Now we need to figure it out, like how fast is it decaying after 70 years. Again, that is the rate of change. So all I have to do is plug in 70 for t. So I'll say n prime of 70. And that's equal to 28 e to the negative 0.028 times 70, and more calculator work. So 3.94. Okay, so we are decaying at a rate of negative 3.94 grams after 70 years. And again, this rate of change, changes obviously. As a matter of fact, it exponentially decays, right? We're going down. But, well, we just use our derivative. And then lastly, so example 1 gets 4 pages here. No, 3 pages. Lastly, D reads, after how long will exactly half of the original 1,000 grams remain? All right. So in order to figure this out, we have our function, n of, okay, so I believe our function was n of t, let's not even guess. That equals to t. Okay, so n of t is equal to n naught e to the negative kt, so negative 0.028 t. So this was my equation, and we want to know how long it will take to for exactly half of the original 1,000 grams to remain. So all I have to do is plug and chug here. So I'm going to have 500. this is how many grams I expect to have at the end. My initial amount in naught is going to be 1,000. And then I've got e to the negative 0.028 t. And then we just solve for t. So it looks like we can go ahead and divide both sides by 1,000. So we have 1/2 is equal to e to the negative 0.028 t. We're going to take the natural log of both sides. So we're going to have the natural log of 1/2, and that's equal to the natural log of negative 0.028 t. I'm sorry, not the natural log of it. The natural log and the e go away. So let's fix that a little bit. Right. And then, well, we have the natural log of 1/2. That becomes, and we're going to put this down here. We can rewrite this as the natural log of 1 minus the natural log of 2, right? From our rules, our natural log rules. Well, we know the natural log of 1 is 0, right? So we're going to end up having the natural log of 2, or rather just the natural log of 2, so the negative natural log of 2. And we're going to divide that by a negative 0.028, and that'll be equal to t, which would be equal to, so the negative natural log of 2 divided by that, so negative natural log of 2 divided by the negative 0.028, and that is a 24.76. Okay. So it'll take approximately 24.76 years to lose half of my isotopes. There we go. And I believe that's it. So that's A through D. And luckily, I'm pretty sure that one is the most tedious one, I think. All right, so it says, therefore, we have the following theorem. So let's snip this, give it its own page. By the way, this little bit on the left side here about how scientists can determine the remains of an animal or plant, it's pretty interesting. I think you should give it a read. I'm not going to read it though. So anyways, from example 1, we have this theorem, and it's just the decay rate k and the half-life t are related by kt is equal to natural log of 2. And again, I won't take my word for it, but everything I looked at on the homework, it looks like we are given the formula, but it's not hard to remember. Kt is equal to natural log of 2, and then these two, well, they're just from that, right? So if we solve for k, we divide both sides by t here. If we solve for t, we divide both sides by k. So kt equals natural log of 2. This is the decay rate and the half-life. That shows the relationship between those two. Okay. And we're going to use that for this particular problem. Excuse me. All right, so plutonium. So we do a lot of chemistry in here, right? So plutonium 239 is a common product of the functioning nuclear reactor, can be deadly to people exposed to it. Its decay rate is about, what is that? 2.8 thousandths, 2.8 thousandths per year, or 0.0028% per year. So what is the half-life? So again, my half-life formula, it was KT, K, and then big T is equal to the natural log of 2. Alrighty. So this is my initial formula, and this is the one I'm going to memorize because it seems to be the easiest. And again, I can solve for the other ones pretty darn easily as well. Well, this is telling me that this particular problem, it's telling me its decay rate. Its decay rate is 0.0028. So again, looking at this particular problem, I've got 1, 2. I've got 2 unknowns. Right? Well, we are given one of the unknowns, so we obviously solve for t. Right? Not only that, but it's wanting to know the half-life, which is the time. So we're going to take this equation and we're going to solve it for t. And again, we don't have to necessarily go back to the notes because, well, we can do this kind of math pretty darn easily. We just have that. So in order to solve this particular problem, we have our time is equal to the natural log of 2 over k, which is, we're going to put this in decimal form, right? So real quickly, just so, because you're gonna have a lot of these on the test, 0.028%. Right? The way the way that we change this from percent to decimal is you just take this decimal and you move over to the left two places, and then of course you get rid of the decimal sign. Okay. So we've got a ridiculous number here. So 0 point, and then that's 4 zeros, 1, 2, 3, 4, 2, 8. Okay, well, what is the natural log divided by, natural log of 2 divided by that? So natural log of 2, 0.4 zeros, 1, 2, 3, 4, 2, 8. Ooh, wow. So plutonium has an insane half-life of 24,755 years. That's a lot of years for it to decay half of it. Okay, and that was example 2. And next up we're going to talk about carbon dating, and again we're going to be using the same formula, so I'll go ahead and put it at the top again. So the initial formula, again, I'm just going to write just this k, let's pick that k, so kt is equal to the natural log of 2. Okay, we're just going to roll from there. All right, so this problem reads, the radioactive element carbon-14 has a half-life of 5,730 years. The percentage of carbon-14 present in the remains of plants and animals is used to determine age. Archaeologists found that the linen wrappings from one of the Dead Sea Scrolls had lost 22.3% of its carbon-14. How old was the linen wrapping? Okay, so we want to figure out how old the linen wrapping is. So we need to figure out what the decay rate is, right? And the decay rate is going to just be K. So in this particular case, we're going to take this equation written in yellow, and we're going to solve for K. And so that, again, is just going to be the natural log of 2 over T. Right. And solving for this, well, my decay rate is K is equal to the natural log of 2 over my time, which is 5730. So 5730. And that's equal to 2 divided by 5730. So, okay, so a nice, good small number here. So we've got 0.000, and we're just going to do 19. Okay. That's the, oh, I'm sorry, I did a natural log of 3. Let's fix that up. 0.00012. There we go. All right, so that's my K value. So what do I do with my K value? Well, we're gonna have to go back to our decay model now because we are decaying. We found our K. Let's go back and I'll show you what I'm talking about. Let's see here. Okay, so this is the decaying equation, and again, looking here, I have P of T, that's one unknown, P naught, that's two unknowns, negative K, that's three unknowns, and T, that's four unknowns. All right. Well, we're gonna have to do something a little fancy here to figure out how to get rid of the unknowns. So I said we had four unknowns, and all we've done is just figured out one. We've only figured out K, right? And we are asked, I believe we're asked for the time. Let's see. Yeah, it's wanted to know how old was the linen wrapping. So we're going to be solving for T. Okay. So if we're solving for T, then we have the N and the N naught. So that makes two unknowns that we don't know. So we're going to do something pretty clever here. Where we at? Okay, we're going to do something pretty clever here. So again, just to quickly recap. One unknown, two unknowns, P of t, P naught, K, and T. We figured out what K is, we're trying to find T. We don't have an idea of the initial amount or what it's at now. All we have is how much it's decayed. So the clever thing we're going to do here is we're going to rewrite this instead as well. First of all, let's introduce the equation so we can have it nice and neat. Let's put it on the next page. Okay, so I want to really get into this because I've seen questions like this in every single math course I've ever taught, and it's always this clever trick that's used. So my equation is going to be n of t. Let's fix that, n of t, and that's equal to some n naught, and then e to the negative kt, and e to the negative k, which was 3 zeros and 1 2. 0.123 1 2 t. Okay, so this is my equation, and I'm going to be solving. I found my k once again. So I found my k, and I'm trying to find my t. What do I do with this n naught and this n? Okay, well, what do those represent? Well, the n represents the amount that we have now, and then the n naught represents the initial amount. Okay, well, we don't necessarily know that information to put it down. We don't know how much of it was there. So the clever thing we're going to do is we know that reading here it says the Dead Sea Scrolls had lost 22.3% of its carbon-14. So if it lost 22.3% of its carbon-14, then that must mean that there are 77.7% of the initial amount, right? That makes sense because I mean if it's only lost 22.3, that means it is that there's 77.7% of the initial amount. And then we can proceed and put this into the equation like this, to the negative 0.00012t. Right? And hopefully you see the clever thing we just did there, right? Well, let's go ahead and instead now rewrite the percentage as a decimal, which is going to be 0.777, and then we can solve, right? And when we solve, well, what do we do? What happens here? If we divide both sides by n naught, that goes to 1, and this goes to 1, and now they're gone, right? So that's the clever manipulation that we did or that we're going to do for this particular problem, and you're going to see it a lot in many of your classes. Every single class I've ever taught with radioactive decay has this particular problem. But anyways, since the n naught's canceled, then I'm going to end up having 0.777 is equal to e to the negative 0.00012t. And then it just becomes one of those problems where we just take the natural log of both sides. So we take the natural log of 0.777. That's going to be equal to negative 0.00012t. And then we divide both sides by 0.00012. Yeah, so we end up with it's equal to t, which is equal to all right, so about 2,100 years. So 2102. Right. So that's how long the Dead Sea Scrolls have been, um, how old they were rather, or how old the linen wrappings were. And if these were found, I think these were found in like the 1920s or 1930s, and so the Dead Sea Scrolls were written in the time before Christ. So that's pretty cool. I think the manipulation that we did there is really cool, and a lot of higher mathematics is uh, derived from clever manipulations like that. Alrighty, so I think three more examples. So bankers and financial planners are often concerned with problems like the following. The business we have present value. So following the birth of their granddaughter, Doug and Andrew wanted to make an initial investment P naught that will grow to $10,000 by the child's 20th birthday. The interest is compounded continuously at an annual rate of 4%. What should the initial investment be? Okay, so using our equation of P is equal to P naught e to the kt, e to the kt. So using our equation that we've seen before, we need to figure out uh, my initial amount, right? Well, we have the rate, which is 4%. So we have k taken care of. So again, let's do this. So we have one unknown, two unknowns, three unknowns, four unknowns. Well, we're told what k is. We're told k is 4%, so that takes care of one of them. We're told we're told what we want to figure out, or what we want at the end, which is $10,000. So we have that figured out. And we also know that we're doing it in 20 years, so we have the t figured out. So we're given every single one of the unknowns. So this is just a simple plug and chug. There's nothing new we have to do. So following along with this equation, right? We want $10,000 in the account, so that is the p. $10,000 in the account. We're trying to figure out the initial amount. So how much should I invest? And then e to the, and then k is 4%, so that is 0.04 times t, which is going to be 20. And, well, I know what 4% 20 is. Sorry. All right, so we end up, if we're solving for p naught, we end up with 10,000 divided by e to the 4% is 0.8. That's equal to p naught, which is going to be equal to, so it's just 1,000 divided by, I'm sorry, 10,000 divided by e to the 0.8. 10,000 divided by e to the 0.8. 44.93. So we need to invest about 44.93. Doug and Andrea need to invest about 44.93. So by the time their granddaughter turns 20, that money will have grown to $10,000. So that's a nice little gift. And that was a pretty easy problem. All right, so Newton's law of cooling. So we're just going to snip all of this. All right, so these next two, there are a couple steps involved. Alrighty, so first let's talk about Newton's law of cooling. The law of cooling, it's something you're familiar with. Obviously, you probably didn't know that there was an equation attached to it, but something cools down to the room temperature, right? So consider the following situation. A hot cup of soup at a temperature of 200 degrees is placed in a 70-degree room. The temperature of the soup decreases over time, T, according to a model known as Newton's law of cooling. And following along with these equations, the temperature T, so capital T is the temperature of a cooling object, drops at a rate proportional to the difference, T minus C, the difference, where C is the constant temperature of the surrounding mediums, kind of like room temperature. Thus we have the derivative is going to be equal to a negative K times the temperature we want, or rather the difference of the temperatures, the temperature we have and the surrounding medium, and of course for k is greater than 0, the function that satisfies this equation. So when we say the function that satisfies it, again, this is the function that we can put into here, kind of like we did with example 1. So that's what we mean by the function that satisfies it. And again, it's differential equations, but here we are. Alrighty, so example 5, scalding coffee. And of course, I'm pretty sure if you haven't heard about it, there was a lady who got to sue McDonald's back in the early 90s because she spilled coffee on herself. But it wasn't just hot coffee, it was scalding hot coffee. And she won a pretty penny too. So McDivitt's Pie Shops, a national chain, finds that the temperature of its freshly brewed coffee is 130 degrees. The company fears that if customers spill hot coffees on themselves, lawsuits might result. Room temperature in the restaurant is generally 72 degrees, so the temperature of the coffee cools to 120 degrees after 4.3 minutes. McDivitt's decides that it is safer to serve coffee at 105 degrees. How long does it take? How long does it take a cup of coffee to cool to 105 degrees? So, using these formulas that we have up here, we have to first figure out um, this function here. And looking at it, all right, we have t, again, big T, and then, which is the same thing as saying big T of t, right? It's just that's the unknown. So big T, that's one unknown. A, that's two unknowns. K, that's three unknowns. T, that's four unknowns. And C, that's five unknowns. So we have five unknowns here, right? But in the problem, we are told one of the unknowns, which is the temperature of the coffee. So that's 130, so that's going to go with T. So now instead of five unknowns, we have four unknowns. We also have the temperature of the surrounding medium, or in this particular case, the room temperature. So now instead of four unknowns, we have three unknowns. And we also need to figure out, so the unknowns now are A, K, and T. Right? We're trying to find T right now, but we also have to figure out what A and K are. So in order to do that, we have to do something, again, kind of clever, but this isn't necessarily so clever that you have to use it or you have to kind of think of something like this for problems. This is just going to be this is something you'll do for all of them, honestly. Every single one of these problems, when you have an initial time, what that tells you is you can put 0 for t, and by putting 0 for t, that immediately wipes out k, right? Because it doesn't matter what k is, k times 0 is 0. So I say all that to say this. So let's go to here. We have t of t is equal to a e to the negative kt plus c. Okay, so let's go ahead and start filling in the blanks here. So the temperature of my coffee is 130 degrees. So that's going to go here. Excuse me. A, we don't really have a way to solve for A, right? A is just some sort of constant that we're multiplying it by. And then E, of course, E is just not a variable, but a number. And then K, we don't know what K is either, all right? And that's super unfortunate. But what we do know is that if the temperature of the coffee is 130 degrees, then that must mean that the time here must be 0 minutes, right? Because that is as soon as that coffee is freshly brewed. It's right off the bat. So at time t equals 0, my coffee is 130 degrees. And then of course plus C, which is the surrounding medium or room temperature, which is 72 degrees. So we're going to have to just solve for A here, and we can do this in our head, right? This goes to 0. E to the 0 is 1, so this is just basically 1, right? So A times 1 is 1. And so all I have to do is subtract 72 from both sides. So subtracting 72 from both sides, we end up with 58 is equal to A. Okay, cool. So we have A now. So that helps us out. So what do we do with the A? Well, now let's rewrite this equation. So we're going to rewrite this equation as T of T is equal to 58. 58 is now A. e to the negative kt plus c, which is 72. Okay, so now we're going to have to find out what k is. So once we found a, now we have to find k. Well, again, we in this particular case now we have two unknowns. This one, well, I'm sorry, three unknowns. Uh, big T, little t, and k. So let's go ahead and put this on the next page, and we'll resume from there. Okay. So again, we have three unknowns. 1, 2, 3. Well, lucky for us, on the problem, we are actually given some information here. Well, we use the initial time at time equals 0, t equals 0 to say that the coffee was at 130 degrees. Well, now, where are we at? So now it reads the temperature of the coffee cools to 120 degrees after 4.3 minutes. So we're going to put 4.3 for t and 120 for 4.3 for little t and 120 for big T, and then we're going to figure out what k is. So we're just filling in blanks here. So again, it cools to 120 degrees, and then we've got 58 e to the negative k, and then t was 4.3, I think. Hopefully, we'll see. Yeah, 4.3. And then we solve for k. So every unknown is now taken care of, and we solve for k. So let's see. We're going to subtract 72 from both sides, so that's going to be 48, and then we're going to divide both sides by 58, so it's going to be 48 divided by 58. That's going to be equal to e to the negative 4.3k. We're going to take the natural log of both sides, and we don't necessarily have to take the natural log. We don't have to do what we did earlier. We can just keep it as a natural log of 48 over 58. So what I mean by that is, earlier we had where was it? Here. Earlier we had the natural log of 1/2, and we could have just kept that the way it was, but since it's a natural log of 1 minus a natural log of 2, I know that the natural log of 1 is 0, and I can proceed there. Well, it's going to stay circled now. In this particular case, I'm not going to go natural log of 48 minus the natural log of 58 because there's really no point. The natural log of 48 and the natural log of 58, they're actual numbers. Nothing's 0, nothing I can take out. So I'm just going to keep that the way it is. So continuing to solve this equation, I'll take the natural log of both sides. So I'm going to end up with the natural log of 48 over 58. And that's equal to 4.3, rather negative 4.3, 4.3k. And then we divide both sides by negative 4.3. So we're going to have, put this in green, to kind of differentiate natural log of 48 over 58 divided by negative 4.3. That's going to be equal to k, which is going to be equal to. All right, so this is definitely one where when you put it into the calculator, you are very precise with your division symbols. So my k is going to be about, you always put that equal sign there. It's going to be about 0.044. Whew, okay, so we have now figured out what A is and what K is, and now we can finally figure out the problem, or the solution to this particular problem. So let me see if I can quickly memorize this. So we're going to have 58 to negative 0.044. All right, so I'm probably going to flip back and forth. Oh well. Oh, we have 9 people in here. Dadgum. So here we go. My equation now is going to be T of T, so T of T, and that was equal to, and I've already figured out, so 58 e to the negative 4.3k. 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 58 e to the negative 0.044, I think. Yeah, 0.44 T, and then plus the room temperature, which was 72. Whew. Now we have pared this down to only two unknowns. One unknown, two unknowns. The temperature and the time. So now we can finally figure this out. And I then forgot what in the world this problem is asking. So let's go back. All right. So the temperature coffee cools. McGibbous size is safer to serve coffee at 105 degrees. How long does it take a cup of coffee to cool to 105 degrees? So it's one thing to know how long it will take. So we're always going to be solving for little t. So we're going to have to do here is just solve for little t. So we're going to replace the big T with 105. 105 is equal to 58 e to the negative 0.44 little t plus 72. All right, so let's begin. So 72, so 70 minus this. I'll try and do some quick math. So we're going to have 33 and then divided by 58, and that's equal to e to the negative 0. So it's be 0.44. 0.44 t. So 0.44 t. We're going to take the natural log of both sides. So we're going to have the natural log of 33 over 58, and that is equal to negative 0.44. Did it again. Negative 0.044 t. And then we're going to divide both sides by negative 0.44. So we're going to end up with, let's put this in green. Is approximately 12.8. So 12.8 minutes. Holy smokes. Okay, so this is how long we need to let the coffee sit out before we serve it to the customer. A 13-minute wait. Okay. Well, I mean, no, the customer doesn't have to wait. It's just once you brew it, it waits. All right. So that was an adventure, and we're gonna go on that adventure one last time with this. And I think this is pretty darn cool. This is a really cool example. Um, when I was growing up, CSI was really big. The original CSI, and I remember going to class and everybody wanted to be a forensic scientist. And this is kind of just like a throwback to one of those times um, where even I wanted to, right? But turns out I don't really like dead bodies. Anyways, a body is found slumped over a desk in a study. The coroner arrives at noon, immediately takes the temperature of the body, and finds it to be 94.6 degrees. She waits 1 hour, takes the temperature again, and finds it to be 93.4 degrees. She also notes that the temperature of the room is 70 degrees. What was the approximate time of death? All right, so in order to figure this out, we have to use our formula from before, which is T of T, which was equal to AE to the negative KT T plus C. All right, so again, let's go through the unknowns here. We have one unknown, two unknowns, three unknowns, four unknowns, and five unknowns. All right, so starting out, this says the coroner arrives at noon, immediately takes the temperature of the body. So that immediately takes the temperature of the body tells me that my time is going to be 0. So that's going to immediately take away these two right here. So that's going to take away those two unknowns. Uh, the temperature of the room is 70 degrees, so take care of that unknown. The initial temperature of the body was 94.6 degrees. That takes care of that unknown. So this lines up really nicely. I'm going to have to find A first, and then I'm going to have to find K. And you're going to notice that as a theme, because that's what we did in the previous example. We had to find A, and then we find K. The reason we don't find K first is because, well, we need to take K out, right, with the initial times. Since the initial time is 0, K times 0 is 0, and that takes the K out. So we have to find A, and then find K, and then solve the problem. You're going to be doing that for all of them. Find A, find K, solve the problem. So here we go. Find A. The temperature of the body was 94.6 degrees. And that's equal to A e to the negative k. We don't know what k is, but that's okay because my t is 0. And then plus the temperature of my surrounding area was 70 degrees. Okay, so solving here, again, this is pretty easy mental math. This goes away. Well, yeah, it goes away. It's 0, and then e to 0 is just 1. So my problem is just going to be 24.6. So 24.6 is equal to A. So we figured out what A is. Okay. Now we have to figure out what K is. So I'm going to have to rewrite this equation. T of T. I'm rewriting this equation, but I'm getting little pieces of the puzzle here. So 24.6 e to the negative kt plus c. Right. So now we have to figure out what k is. Well, here it reads, she waits 1 hour, takes the temperature again, and finds it to be 93.4 degrees. Okay, so solving for this, well, now the temperature is 93.4 degrees, and then 24.6 E, and then we don't know what K is, but that's okay in this particular case. All right. T was 1, right? She did it in 1 hour. 1 hour later, 1 times K is just going to be K, so negative K. And then the surrounding temperature is still 70 degrees. And we're going to have to solve here. Let's just do it on the next page. So solving here, we subtract 70 from both sides. We end up with 23.4. So 23.4 is equal to 24.6 e to the negative k. We're going to let's go ahead and divide both sides with 24.6. So we've got 23.4 over 24.6. That's equal to e to the negative k. Yeah, it's pretty easy stuff here. We're going to take natural log of both sides. So natural log of 23.4 over 24.6. That's equal to negative k. And so that means k is going to be approximately okay, so it's going to be approximately a, and then keep in mind we have to write it as a negative, okay? So, well, I say as a negative. This is negative 0.05. And then if we're solving for k, then we multiply both sides by negative 1, so it becomes a positive 0.05. Okay, so now we have our k. So now we can proceed with actually solving this problem. So put up a new page, and I don't even remember the equation, so we're just going to have to kind of do this the hard way. So we have T of T is equal to, oh shoot, I forgot the A, 24.6 e to the negative. All right, so the negative sign is always going to be there, so it's going to be a negative 0.05 T plus C. So this is going to be our equation where we figure out how long the body has been laying there. So she waits 1 hour, takes temperature again, that's what we did. She also knows the temperature, okay. So what was the approximate time of death? So we need to figure out the approximate time of death, and in order to do that, we have to figure out, t, right? Time, we have to figure out how much time has elapsed. Alrighty, so the um, the temperature of the normal temperature of a body is 98.6 degrees. So that is what we're going to be using for our temperature of a body here. So the normal temperature is 98.6 degrees. And then, well, that's horrible. And then we have this 24.6 e to the negative 0.05 plus the surrounding, I think was it 70 or 72? I forgot. So 70. And we just solve for t. All right, so we're going to subtract 70 and divide by 24.6. So we're going to say 28.6 divided by 24.6. 0.6 divided by 24.6. And that is equal to e to the negative 0.05. We take the natural log of both sides. And that's equal to, forgot to put the t there. It's equal to a negative 0.05 t. And we divide both sides by negative 0.05, and we'll get our t. So we've got t is equal to, and we'll do approximately. T is approximately natural log of 28.6 divided by 24.6 divided by negative 0.05. So it's going to be negative 3.01. So to wrap all this up, our coroner, she arrives, she takes the temperature of the body, and then an hour later she takes the temperature of the body again, just to get an idea of the constants involved, the surrounding temperature and things like that. And then from there, we're able to derive that this body, all right, so she arrived at noon, from the initial time that we took the temperature, the body had been there for 3 hours. So if she arrived at noon, then this poor fella probably studied himself to death at 9 o'clock in the morning. And that does conclude his lecture, but I'm pretty sure there's a good section summary here. There always is. There we go. Section summary, and we're done.